Greetings, ladies and gentlemen, and welcome to your Chapter 26 lecture. Today we will be talking about electromagnetic radiation, or the phenomenon that we commonly call light. Now, by this point we've realized, because we talked about it already, that electromagnetic radiation is actually take the form of waves. They're actually a wave-particle duality, so they actually display characteristics of both. But we'll come back to that in a little bit in a future chapter. As a matter of fact, it's not just one wave, it's actually two. So this would be like an electric wave and a magnetic wave that are coupled together. So if the electric wave is oscillating this way, up and down, the magnetic wave would be oscillating in and out of the board, and they would both be traveling together to the right in three directions that are all mutually perpendicular. Now typically, the electric field portion and the magnetic field portion oscillate together in phase with each other. I don't really much care for how the author describes why it is that light has to move at the speed of light, nor do I care for one of his incongruencies, and that is that James Clerk Maxwell discovered the speed of light in 1862. That is not correct, because a guy named Romer actually figured this out in 1676. As we can see, that's like 200 years earlier. Now, plenty of astronomers and physicists, mathematicians, and what have you, over the years following Romer's discovery, refined the number over and over until Jean-Baptiste Joseph Delambre got really close in maybe 1802, or Hippolyte Fuseau maybe in 1849. What James Clerk Maxwell did in 1862 was he unified our understanding of electricity and magnetism by using those four equations to show that electricity and magnetism really are one phenomenon, inseparable and indivisible. Now, we commonly call the four equations that he put together to describe electromagnetism Maxwell's equations, but he didn't actually write any of them. However, he did sort of fill in the blanks and do all of this sort of necessary fundamental mathematics to show that they were all part of one system. And nobody else was able to do that. In any case, I know I'm picking on the author of this book a lot, but he probably wrote this book back in like the 70s and never took the time to go back and correct his boo-boos. It is also to say that our understanding of the speed of light comes from Einstein's theory of relativity, not from James Clerk Maxwell, nor from conservation of energy, or what have you. It came from Einstein. One of the basic tenets of relativity is that light happens to be the ultimate speed limit in the universe. Now, in any case, if you remember from our basic understanding of wave mechanics, wave speed is equal to frequency times wavelength. And so, you can take electromagnetic radiation from any source. It doesn't matter if it's the ultraviolet light coming from the sun, or gamma ray bursts coming from a distant high energy source like a supernova event or something along those lines, or your favorite FM radio station. Now, I know nobody listens to the radio anymore unless something in their stereo is busted, right? But FM radio generally has a range of frequencies from 88 megahertz to 108 megahertz. That's why you'll see stations like 89.1, 106.1, whatever, blah blah blah, 92.5, that kind of thing. Those are all numbers because they fall in between these two upper and lower bounds. Now, you can of course multiply the frequency of any of these sources or any other electromagnetic sources like the light and multiply it by its wavelength. And that will always give you the wave speed, which of course is the speed of light. in all cases for electromagnetic radiation, that of course being 3 times 10 to the 8th meters per second. So, long story short, the product of the frequency times wavelength for all electromagnetic radiation is always 3 times 10 to the 8th meters per second. Electromagnetic radiation is special in that its frequency and wavelength do not exactly dictate the wave of the speed. Rather, it's sort of the contrary. The wave speed is always 3 times 10 to the 8th meters per second. Now, the author goes on at some length about how electromagnetic radiation propagates through transparent media like water and glass, diamonds, etc. However, the author goes about it in a really terribly roundabout, beating about the bush kind of way. A much more concise approach, especially since we already have the expertise with it, is to think about our good friend the gas lamp. Now, we had a gas lamp demo in class, but I've also included a link to a gas emission lamp demonstration video on the chapter 26 lecture page. So if you need to pause it to go and look, now is probably a good time for that. Okay, so why was it the hydrogen lamp only gives off a few colors of light? Well, because the hydrogen atoms, which have quantized energy levels, right, will absorb and then re-emit the light. Optical media like glass, water, diamonds, plastic, etc. also absorb and re-emit light. Now, they're much more dense with atoms that reabsorb and re-emit light than, say, the vacuum of space. And so light moves more slowly in glass or plastic or water or things like this. Because that reabsorption and re-emitting process takes a little bit of time. On the other hand, air is very diffuse, right? And it's got a very sparse amount of particles compared to something more dense like water. And so air doesn't slow down too much going through the air as compared to something like glass or diamonds. The author also describes that glass is opaque to infrared and infrared electromagnetic radiation, similar to how our atmosphere is opaque to most electromagnetic radiation except visible and radio. While it is true that our atmosphere is opaque to most parts of the electromagnetic spectrum and only generally visible light, which obviously visible light has to get through our atmosphere, otherwise we wouldn't be able to see it, right? Light from the sun wouldn't get in. And also radio, which is why radio astronomy is so effective at scouring the universe for answers. However, this thing that the author said about UV and infrared light is not correct. Yes, most glass blocks UVB, the kind of ultraviolet light that you get a sunburn from. So it's hard to get a sunburn if you're sitting in your car, as long as you have the window up, right? And if you don't believe me, think about which arm has that farmer's tan. If you're the driver, it's going to be your left arm, right? Because all of our driver's side seats are on the left-hand side, and so the arm that can hang out the window is the left one. That's where you get your farmer's tan, right? The right arm, however, because it stays in the car, doesn't get so much of a tan. In any case, UVA, the kind of ultraviolet light that causes cancer, is not blocked by UV glass, unless it is properly coated to do so. For that reason, lots of sunglasses are UVA coated, and the ones that are plastic that aren't necessarily UVB protected in and of themselves because they're not glass, are usually also coated against UVB, so you can't, roast your face and your eyes just standing out in the sun. As a matter of fact, fluorescent light fixtures, the ones that are in our classroom, give off a small amount of UV light, and they're also made of glass. It's apparently only about 3% of your daily dosage of UV light to be sitting under one of those one of those fluorescent lamps with the small amount of UV that they emit. For about the time that we'd be sitting in class together. However, that's enough to make one UK-based research group recommend that you wear sunscreen if you sit under fluorescent lamps too long. Also, glass does not block infrared light. If that was true, the infrared radiation from a heat lamp wouldn't get through the glass to keep your lizards warm or whatever you got in your atrium, whatever you call where you keep a snake or a lizard. In any case, not everything is transparent to electromagnetic radiation. For example, we do not absorb and re-emit light. Sure, sometimes we can reflect it from some of our surfaces, otherwise you wouldn't be able to see my hand, right? But most of the light that hits us gets absorbed. What happens to that light? Well, it would violate the law of conservation of energy if it was just destroyed or went away somehow, right? The atoms in our clothes and bodies absorb this energy and it vibrates the atoms. And if you remember, causing atoms to vibrate or have more kinetic energy means an increase in temperature. Long story short, we absorb the light as heat. And that's why, if you wear black, right, you're reflecting fewer wavelengths, fewer frequencies of light, and you're absorbing more of them. Which is why you want to wear black on a winter day to stay warm. In any case, that also means that not everyone has the same resistance to sunburns. If you have darker skin, then the melanins in your skin act as a natural defense against sunburns and skin cancer. However, you're more prone to having a vitamin D deficiency. If you have fairer skin, you probably already know that you burn easily, but you get your vitamin D more easily from the sun. If you get a tan, however, your melanocytes can put more melanin in your skin and up your resistance to UV. However, this requires that you up your exposure to UV to begin with. So it's sort of a catch-22. In any case, let's talk a little bit about shadows, shall we? Now, unless something interesting happens, for the most part, light travels in a straight line. In our last diagram, we saw the electromagnetic wave, right? The electric wave and the magnetic wave traveling this way together, right? In one straight line direction. Now, some things can happen. Sometimes matter can warp the curvature of space-time, like in a strong gravity well around a star or a black hole or something like that. Light can pass through it and curve its path somewhat. But also, light can pass through a refractive index, things like water, glass, plastic, and that can cause light to bend as well. If something blocks or absorbs light because it's opaque to it, some light will be missing, and that gives off this funny thing we call a shadow, right? Where there was normally light before, now it's gone. To better discuss this phenomenon, let's discuss a set of familiar cases, shall we? How about eclipses? When an object as far away and as large as the sun sheds its light on us, we can block some of its light on the moon. So let's say the moon's here, right? And I'm going to draw it like this because we're going to put the sun over here, right? The sun is huge, not to scale, obviously, but very, very far away. Here's the Earth. Like I said, obviously not to scale. But let's say that the sun is far enough away that actually, let's make the sun far enough away that it's only about yay big, or it appears that big in the sky. It's not actually what's going to happen, right? There's the dark side of the moon, the one that's facing away from the sun. Okay, so here's light from the top. Here's light from the bottom. And actually, if I drew the moon here instead, there is no light from the top that's going to hit the moon now. there's no light from the bottom that's going to hit the moon now either, right? This cone is dark from the bottom, this cone is dark from the top. They overlap here. This is a very dark shadow right here. Now what's happening, let me erase the lines again. What's actually happening, the sun is shedding its light on the Earth is blocking the light, so this region is dark. What do we call that? That's a lunar eclipse, right? The moon gets dark. In any case, if you go and look at a picture of a lunar eclipse, especially a partial lunar eclipse, you see like the moon with its surface, there's flat seas and then there's some craters and blah blah blah. And if you look at the shadow that the Earth casts on it during a partial lunar eclipse, you can see very easily, very readily, that the shape of the Earth's shadow is round, meaning the Earth has to be round. So take that, flat earthers. In any case, the really, really dark part in here, the part of the shadow where it's really dark, where all of the direct light gets blocked out, that's called the umbra. And the parts out here where it's not quite so dark is called the penumbra. Now this is not to scale. Obviously the sun would be much, much farther away. The Earth and the moon would be very close by comparison. The moon is something like about 350 to 400,000 kilometers away on the average, whereas the sun is something like 150 million kilometers away, very, very far, right? It takes light about a second to get to the moon. It takes light about 8 minutes to get here from the sun. In any case, let's reverse this configuration now. This would be, lunar eclipses only happen during the full moon, when the side of the moon that the sun illuminates is facing toward it. But let's put the moon where it should be about 2 weeks later, here, during the new moon phase. Now what's going to happen here, whoops, is there will be just one very, very dark spot where the umbra touches the Earth. And that is where you can see a total solar eclipse. All the rest of the other parts, it'll look like a partial eclipse. And that covers a very large part of the surface of the Earth. Again, not to scale, but that's the long and short of it. This is what we call a solar eclipse, when the moon blocks out some of the light that the sun was going to shine on the Earth. Now, like I said, there are partial eclipses, like where you see just some of the light get blocked out. There's total eclipses where you see everything get blocked out. Sometimes, if the moon is too far away, we get a funny thing here. It looks like the moon is too small to cover the entire sun if it's too far away from the Earth. And what that looks like, instead of seeing the whole sun get blocked out by the moon, because it's farther away than usual, it blocks out most of the sun, but there's still a bright ring around the edge. It's called an annular eclipse. Now sometimes, and it actually happens pretty often, that the moon, because it's going closer and farther away and closer and farther away as a result of its really funny kind of orbit, sometimes an eclipse will start as an annular eclipse and become a total solar eclipse, or start as a total eclipse and become an annular eclipse. Those are called hybrid eclipses, and those actually happen pretty often. About half of the eclipse events that we usually call a total solar eclipse are hybrid eclipses. In any case, now that we understand a little bit about light and shadows and so on, let's talk about how you process the information that we know as light. Your eye is a pretty interesting piece of machinery, honestly. But your eye has some difficulty processing light in some ways. This gives rise to a series of interesting effects, starting with this thing called a blind spot. And I'll talk about why that exists in just a second. But if you want to toy around with your blind spot, just so you know that it's there, take a piece of paper, draw an X on it, and draw an O about 2 inches apart or so. Close one eye and look at the X, and then bring the paper close to your eye until the O disappears. When it kind of fuzzes out and you can't see it so well, the O is at your blind spot. Now, why is the blind spot there? What does it mean? Well, your eye is kind of this funny thing. You call it an eyeball because it's mostly spherical, right? There's this cornea thing on the outside. There's a hole in the middle here called a pupil. And there's this thing here called a lens, essentially. Light will come in here through the lens and it'll make an image on the very back, this place called the retina, which is basically like a screen. Now there's a nerve that comes in here, your optic nerve, and any light that hits that doesn't have the receptor cones and rod structures that sense light intensity and color. And instead, this is where the nerve hooks up to your retina, and so there's a blind spot there. But regardless of the fact that there's actually a blind spot there and that part of your retina can't actually see anything, there's no blocks missing from your vision, because your brain is able to interpret most of what you're seeing and it kind of fills the gaps in. And that's why there are these crazy things called optical illusions. Now, some of these, and I posted all of these in the chapter 26 lecture page, but some of these, once you see them, you can never unsee them, and they will never be optical illusions again. Like the shiny legs, those are actually painted legs. And the two faces that appear to be looking at each other, they're actually not, right? They're both looking straight forward. And once you see that, you can never unsee it. But most of these rely upon the fact that your brain is filling in the gaps of information. There's that really famous one, they call it the Pac-Man optical illusion, where there's a bunch of dots in a circle and one is missing, right? And the one that's missing slowly progresses around the circle. If you just stare in the middle, I'm not going to ruin it for you, but something really interesting happens. In any case, a lot of these optical illusions are just that, your brain filling the details in. Now, that's it for chapter 26. So I hope you've enjoyed this, and please make sure you take the quiz for understanding. I'll see you for chapter 27.